Hi, everyone. Can you all see the whiteboard?
Yes.
Okay. What answers did you get for the first question? Okay, good. Most of you got the right answer, 37, or all of you got 37. Dhanush, can you explain?
So the first half of the numbers, since it said too low, you can just cross all of those out because those won't work. And for the remaining numbers left over, there's only four numbers that are one off. So they're 36, 38, and 47, 49. The number between those numbers are 37 and 48. So 37 is prime and 48 isn't prime. So it has to be 37.
Good. Yep, that's correct. So let's just review from this list once more. Okay, so we know the list of all the guesses. There's, let's see, 10 total choices or 10 total guesses. At least half guessed too low. That means the first 5, this is in sorted order, are too low. So that means it must be at least more than 36. So we know it has to be 36, and we can kind of get rid of the bottom 5 guesses. So now we know that it has to be above 36, and we know that 2 of the people are off by 1. So that means that it has to be more than 36 and within 1 of 2 of the guesses. Now, in order for this to be true, that means the 2 guesses have to differ by 2, such that this one would be in the middle of those 2. We see the pairs that could happen is 36 and 38. So 37 would be in the middle, or 47 and 49, 48 would be in the middle. So either 37 or 48 could work, but we have this last condition. The age is a prime number. 37 is a prime number. Its factors are only 1 and 37. 48 is not, because 48 has factors of 2, 3, and so on. So 37 is the only prime one. So 37 is the answer. And looks like most of you got it. Any questions on this? Okay, let's move to the second one. Okay, good. 2500 is correct. Let's see. Neil, can you explain?
Okay, so first, so I actually did a graph for this problem, a table. And so it says a car has 4 tires and 1 spare tire, and each car can travel 2,000 miles. So basically, we have to find out so I tried to get each tire the same, each tire go the same exact distance. So I basically did, I made a graph, and it's the first tire, the second tire, the third tire, the fourth tire, and the 5th tire. And I put it in a table.
Okay.
So for the first tire, I did 500 miles. So for each tire, I put it as 400 first. No, wait. So that I put each tire as 500. So first I made each tire go 500, but not the spare tire. And then So I basically started subbing the spare tire in for the first tire, the second tire, the third tire, the fourth tire, and the fifth tire. So each tire went 500 miles. So the first 4 tires went 500 miles, but then the spare tire, it didn't go yet. So then I subbed the spare tire for the first tire, and then the spare tire was going 500 miles, and then the rest of the tires were the second tire was 1,000, third one was 1,000, fourth one was 1,000, and the spare was 500. And then I subbed the spare in for the second tire. So the first one was 1,000, the second one already went 1,000. So the spare one already went 500. So when you subbed it in, it went another 500. So 1,000, 1,500, 1,500, and 1,000 for the spare. And then I subbed it into the third one. So I got 1,500 for the first, 1,500 for the second, 1,500 for the third, and 2,000 for the fourth. And then for the spare, I got 1,500. And then last I subbed it in I didn't sub it into anything. I just put them all. Oh no, I subbed it into the fourth one. I subbed it into the fourth one, and then I got 2,000, 2,000, 2,000. So by then I realized that all of the tires were going the same miles. And then that was after 5 full 500. So that all of them became 2,000. So 500 miles. So that's basically it. So then there was 5 different times that it took to do it. So 500 times 5 is 2,500.
Okay, good. Yeah, so this works. So the idea here first is, okay, let's try to think about a way. So there's a few ways of doing it. Let's go over this method first. So you have the 4 original tires and 1 spare tire. So let's think about a way of making sure that you don't wear any tire more than the others, and to still use up 2,000 miles on each tire. So the way to do this is, first we'll think about, we drive 500 miles with the original 4 tires. After the 500 miles, we switch out the first tire for the 5th tire, or the spare tire. Now we drive another 500 miles. So what happened here, after the first 1,000 miles, the second, third, and fourth tires have 1,000 miles of wear. The first and fifth only have 500 miles of wear. Okay, so now after another 500 miles, we'll switch the second tire with the first tire. So now the second tire will be left out. We'll use the first, third, fourth, and fifth tires, drive another 500 miles. And similarly, basically we want to skip one of the tires for 500 miles each. So the next time when we switch them out, we switch now the second and third tires, keeping the third one as a spare, using the first, second, fourth, and fifth, drive for another 500 miles. And we see we're almost even at this point, except for the fourth tire has already been used for 2,000 miles. So we can now use only the first, second, third, and fifth tires, drive the remaining 500 miles. Now we see that all the tires have been used for 2,000 miles. And we've been able to drive 2,500 miles, because 500 with the first set, 500 when we subbed out 1, and so on. And we're able to drive a total of 2,500 miles, even though each tire can only use 2,000 miles, by subbing them out in the right way. So this is one way. We've shown kind of how we can drive 2,500 miles. But one thing that might not be immediately clear is, why is 2,500 the maximum? And this relates to another method of doing this. Did anyone else have another approach?
Yeah, so because there's 2,000 miles on each car, and tire, and there's 5 tires, including the spare, 2,000 times 5 is 10,000. And then because there's 4 tires on the car at all times, you divide 10,000 by 4 and you get 2,500.
Good. Yeah, that's exactly right. So this is a kind of maybe a simpler way to think about it, and then kind of maybe build back to this approach of how do you actually construct a way of doing this. But think about this: when I drive a total of n miles in a car, if you think about the wear on the tires, right, that'll be the same number of miles on each of the 4 tires, right? So in this case, if each tire can go a maximum distance of 2,000 miles, if I think about the total wear on all the tires, and if I count, let's say, the mileage on tire 1, the mileage on tire 2, and so on, if I add that up, the maximum will be 2,000 times 5, or 10,000 miles. So if I take the mileage on each of the tires and add them up, it's at most 10,000. Now I know whenever my car goes 1 mile, I have to put 1 mile of wear on each of 4 tires, right? So for the car to go a mile, it takes 4 tires to move forward by a mile. So basically, I can divide this by 4 to get the actual number of miles I can go with this total mileage on the tires. So really the maximum I can do is 10,000 divided by 4, which is 2,500 miles, because I know that the total wear on all the tires, or the total mileage on all the tires, will be 10,000 miles. And moving 1 mile on the car requires kind of 4 miles on tires, because I need 4 tires and each will move 1 mile. So if I take the total mileage on all the tires and divide it by the number of miles to move the mileage on the tires for 1 mile, this says I can actually go 2,500 miles. This doesn't actually tell us how I can go 2,500 miles. And this is one way of doing it. But basically the key idea here is we want to use the tires evenly, right? So we want to use the first 4 tires, but we don't want to use them so much and use up, if we had just gone 2,000 miles together on the first 4 tires, what happens? These are all completely worn out, and we just have this 5th tire that is not used at all, right? So the problem is we can't just drive 2,000 first and then try to switch out the 5th tire, because then the other tires are used up. So you have to do it in a way that we're kind of using every subset of these 5 tires evenly. So how many subsets of the 5 tires are there? Choosing 4 of them. So for instance, I can do 1, 2, 3, 4, 1,
5.
2, 3. Good. Which are the 5?
The first one, the second one, the third, the first, the third, the fourth, and the 5th.
Mm-hmm.
And the first, second, fourth, and 5th. First, second, third, 5th. First, second, third, fourth. First, second, third, fourth, 5th.
Good. Yeah. So there's 5 possibilities. And basically it's removing one of these, right? So either I can remove the first one, I can remove the second one, remove the third, remove the fourth, and remove the 5th. So kind of there's 5 potential groups of 4 tires, and I want to use them all evenly. So with the 5 groups, instead of driving 2,500 miles total, I can divide this by 5 and drive 500 miles with each group of 4 tires. And this ensures it's all even, because every group of 4 tires is kind of used the same amount. So I'll make sure that I total, and we saw how this worked in the beginning. We are using each tire for 2,000 miles total, but we're able to drive a total of 2,500 miles. And we can also compute this with this total mileage method. How much is the total miles on all the tires? Since we always need 4 tires on the car, dividing this by 4 gives us 2,500 miles. Any questions on this? Okay, let's move to the last one. Any answers for this one? Okay, I see one answer. Any others? Okay, I don't see the right answer. So let's actually start off this question in a slightly different way. Let's think about just a simpler question. And we'll try to move from there. Okay, so let's say, what is the probability? So we know that Alice and Bob arrive at random times between 10 p.m. and midnight. So what is the probability that Alice arrives before 10:30 p.m.?
1/4,
Good. Why?
because there is a 120-minute waiting period between 10 and 12. So that is from 10 to 10:30 is 30 minutes. So 30 over 120 is 1/4.
Okay, good. Now that's true. So let me actually like draw this out visually. And I think this will help us also solving the original problem. So this is Alice's time of arrival. It could be anywhere between 10 p.m. and midnight. So now we said that the probability that Alice arrives before 10:30, so let's say 10:30 is somewhere here. So this whole line corresponds to 120 minutes. Before this portion is 30 minutes of that. So it's basically this portion over the entire line, right? Does that portion make sense so far? So this is 1/4 of the entire kind of interval if she arrived before 10:30. Okay, let's take this one step further. What is the probability that both Alice and Bob arrive before 10:30 p.m.?
Is it 1/8?
Close. Why 1/8?
Oh, I just thought you would somehow like divide the 1/4 by 2, but
So it is 1/4 is true for each of them. So while Alice arrives between 10 and 10:30 and Bob arrives between 10 and 10:30. But let's actually go back to this diagram, right? So this we said was the time that Alice arrives, right? Let's actually plot on the y-axis what time Bob arrives. Okay, so we know Alice can arrive anytime between 10 p.m. and midnight. And Bob is also kind of independently arrives at his own time, right? So he could arrive at any time between 10 p.m. and midnight. So I'm trying to kind of pictorially look at what are the possible times that they could arrive. So for instance, so basically what this figure means, so I'm drawing this out as a square here. And essentially each point in the square corresponds to some time that Alice arrives and some time that Bob arrives. So for instance, this point corresponds to Alice arriving at midnight and Bob arriving at 10 p.m. Versus the center point at the center of the square would correspond to 11 p.m. for Alice and 11 p.m. for Bob. Does this make sense?
yes.
Okay. Now, if Alice and Bob both arrive before 10:30 p.m., what part of the square would that correspond to?
So is it 1/16?
Good. Yeah. Can you draw out the part of the square that it corresponds to?
Yeah. Okay, so if this is 11, and same for the other side, approximately,
Sure.
then 10:30, 10:30. So it would be this box right here.
Good. Okay, yeah, that's correct. So yeah, the idea here is that we're thinking about this this square as all the possible kind of things that could happen, right? So Alice picks some time between 10 and midnight. Bob picks some time in between 10 and midnight. And any of these points are equally likely, right? So basically, any point in the square is equally likely, corresponding to some time for Alice to arrive and some time for Bob to arrive. Now, the probability that they both arrive before 10:30 would be, so Alice has to be before 10:30 and Bob has to be before 10:30. So in this entire square, it's kind of this portion here. Now, this is a smaller square. This side is 1/4 of this. This side is 1/4 of this. So in terms of area, the area of this square is 1/16 of the whole square. So we know any point in the square corresponds to some random time of Alice and Bob. And the portion that we care about, or the ones that we're interested in, is this portion here, which is 1/16 of the entire square. Okay, so this is the same idea we need to apply to this problem. How would we apply it to the original question? Okay, so I'm going to remove this inside portion of this square. And let's think about how do we now find the area that corresponds to Alice and Bob meeting if they wait 15 minutes. Okay, so let's say Alice arrives at 10 p.m. exactly. What time should Bob arrive for them to meet?
Anytime between 10 and 10:15.
Good, yes, anytime between 10 and 10:15. So let's draw that out here. So that's something like this, right? Let me pick a different color. Okay, so between 10 and 10:15. So if Alice arrives exactly at 10, Bob could arrive up to 10:15. What if Alice arrived at 10:15?
Bob could arrive at 10:15 to 10:30.
Good. So Bob could arrive 10:15 to 10:30. Could Bob have arrived before 10:15?
10 o'clock too.
Good. 10 to 10:30, right? So imagine if Alice arrived at 10:15, Bob, if he had arrived at 10, he would wait 15 minutes, right? And Alice would come at 10:15, that works fine. If Bob came up at 10:15 exactly, of course they would meet. If Alice arrived at 10:15, she would also wait until 10:30, right? So Bob could arrive anytime actually between 10 and 10:30. Okay, so I'm just drawing some bars here. We'll kind of make this into an area in a bit. Okay, so now let's say Alice arrives at 10:30. What time should Bob have arrived?
10:15 to 10:45.
Good, why?
Because there's the 15 minutes before she arrives, and then the 15 minutes after she arrives.
Okay, good. So that's something like this. Okay. Now what about, let's say 11 o'clock, Alice arrives?
10:45 and to 11:15.
Good. What about 11:30? If Alice arrives at 11:30, what time could Bob have arrived?
11:15 to 11:45.
Good. That would look something like this. And what if Alice arrived at midnight exactly?
$11:45.
Good. That would be something like this. Okay, so if I combine all this, what do you think this forms? If I kind of construct, so I want to find what area within the square corresponds to Alice and Bob meeting.
Is it some sort of diagonal?
Good, yes. So let's kind of draw this out. Let's connect all the tops of these. It's not exactly to scale, but let's say something like this. And with the bottom would also be like this. So this is the area in which they would meet. How do we find this area?
You
Oh.
could find, oh, okay, yeah, you want to say?
So you can find Pythagorean theorem for both of the triangles and subtract that from the actual area of the square.
Good, yeah, and we don't need Pythagorean theorem here, just the area of the triangle is enough. So how do we find the area of the triangle? So good, basically what we want to think about this is it's harder to find the area of this kind of region. But what it is you're seeing you have this entire square and you're removing this triangle and you're removing this triangle. So how long is this side of the triangle? So what time did this point correspond to?
It would be 105 minutes
Good.
or an hour 45.
Good, hour 45 minutes. And so basically what percentage of the whole thing does that correspond to? Is this segment? Or what fraction of the entire area? So we're saying this is 105 minutes and the whole thing is 120 minutes, right?
7/8.
Good. So 105 over 120 is 7/8. So we could either find the area in terms of actually minutes or hours, or we could actually just look at it as a fraction of the entire square. So this is 7/8. What about this segment?
7/8.
7/8. So what is the area of this triangle? So if I have a right triangle with two sides being 7/8,
49 over 128.
good. So it's 1/2 our base times height. So this times 7/8 times 7/8 times 1/2 is 49 over 128. Okay, so now, but we have two of these triangles, right? So what is the total area of the two triangles?
$96 over 128.
98 over 128.
Good, 98 over 128. Does that simplify?
$49 over 64.
Good. Okay, so now what is the answer that we are looking for then? So we have the area of this this triangle and the triangle below. So we have the area of this plus the area of this. We want to find this area.
1 minus that.
Good. 1 minus that. And what would the answer be?
15 over 120, 15 over 64.
Good. 15 over 64. That is the correct answer here. And so the key kind of trick here was an idea called geometric probability. So usually we think about probability separately and maybe geometry separately. The overlap, oftentimes some problems might be like if you're throwing a dart on a dart board, maybe it has to land in some area of that. Those are also geometric probability questions. This isn't immediately like clear that you need some kind of figure or diagram to look at the probability. But typically one kind of clue is when you think about people arriving at random times, right? It's harder to think about maybe like 10, 10:01, 10:02, because when you think about it, it could be any time in between this interval, right? It could be 10:01:01, right? Or 10:01:02. So oftentimes this is represented as thinking about a line segment, right? So when I think about a line from 10 to midnight, then I can say, okay, below 10:30 is some portion of this line, right? And when I'm thinking about two people arriving randomly, it essentially becomes a two-dimensional figure because Bob could arrive anytime between 10 and midnight, and Alice could arrive between 10 and midnight. And I think once you have this diagram in mind, I think it's easier to think about, okay, so if Alice needs to arrive at what time, then what time should Bob have been there for them to meet? And then within this kind of all the possible choices of when Alice and Bob can meet, within that space of possibilities, how much of those, or kind of what percentage of the area corresponds to them meeting? You can think about in this figure, what area would that correspond to? And I think once you have that, then even if you can't find the exact areas, I think this gives you a kind of a mental or picture of kind of the chance that Alice and Bob would meet. And you can see it visually, what percentage of all the possibilities does this happen? Does this make sense? Any questions on this? Okay, that's it for today's class then. We'll see you all next week.
Thank
Mhm.
Thank you. Thank you.
Thank you.
Have a good weekend.
You too, bye.